Good afternoon to all of you. See, in the today's class, module 3, I'll start. I'll be revising the previous two modules also in between. Now you can see here, third module is all about a design of beams. Here you are going to design singly reinforced beams, doubly reinforced beams, and T-beams also. All three will be doing here. So today I'll start with the design of a singly reinforced beam. So at the end of this module, you should be able to design a singly reinforced beam, a doubly reinforced beam, and a T-beam also. T or L beam it is called as. Am I audible to all of you?
Yes, sir.
Okay. So let me start the design. Now, what exactly is design? First of all, what do you mean by design and what do you mean by analysis? You can see this one here. Design of singly reinforced beams. Now, what exactly is design? What is the difference between analysis and design of a beam? Because module 2 was analysis, module 3 is design of beams. Now, how do you differentiate this? Observe here. How you can differentiate these two, analysis and design. Now observe here. As you can see here, when I write like this, beam. When I write beam, you must understand that there are two modules on beam, module 2 and module 3. Now what is module analysis? This is first module 2 is analysis. Then module 3 is design. Now how you differentiate between analysis and design? Observe here. In analysis, what we have done, I'll tell you. Observe. You can unmute. Those who are having this problem, you unmute it. In analysis, what we are doing, I am explaining now. After that, I'll start the design part. In analysis, you can see here. In analysis, the cross-section dimensions of the beam are given AST value. How many bars of what diameter is given? You are calculating the moment of resistance and what is the safe load that the beam can carry. So whether it is an analysis of singly reinforced or doubly reinforced beams, we were calculating cross-section dimensions were known to us, area of reinforcement was known to us, AST value. We were just trying to find out the moment of resistance as well as the safe load the beam can carry. Now, in case of design, reverse will happen here. You have to design means you have to fix the cross-section dimensions for the given span. Here, what is given, you observe here. What is given here is simply span is given and the boundary conditions. For example, what is given, I'll write it. Observe here. What is given in case of design? Just observe. Here in analysis, cross-section dimensions B and D are given, number of bars are given, all data will be given. You are calculating moment of resistance and safe UDL. Now here what is given here is, it is the boundary conditions are given. Boundary conditions means whether the beam is simply supported or cantilever. This boundary condition is given. Okay, either it is simply supported or it is cantilever. It will not be fixed in this particular subject. Fixed beams and windows, they are not there in the syllabus for this particular semester. Either it will be simply supported or cantilever beam will be there. So what I call these two together as boundary conditions. Boundary conditions can be simply supported or cantilever. Now this will be given. Next is load is given or you have to calculate from the data. Load is either given. Here in the analysis what we did, load was calculated as a last calculation. Safe load was calculated as a last calculation. Here load is given or some other data will be there from which you can find out load. Either it is directly given or indirectly given. So boundary conditions, load. Next one is, next thing that is given is span is given in design. They have to give the span like 4 meter, 6 meter like that. So span has to be given. Then apart from this, material used, whether FE 415 is there or FE 500 is there, they have to clearly mention that one. Now I'll write it. Just observe. FE grade of steel and concrete will be given. Either it is 415 or 500 is given. You have to be careful. What are the different constants if FE 500 is used instead of FE 415. Now you can see here. Next one is M20. So it means boundary conditions are given, simply supported or cantilever. Load is given or it can be calculated. That much data will be there. Span they have to give. Materials used, grades of the material. This is important. This one you have to be careful whenever the material is given. So usually this is the combination that is given for all the problems. In the question paper, what they are doing, for some problems FE 500 they are giving, for some problems they are giving M20 like that. So you have to be conversant with both combinations. Even M25 FE 415, M25 FE 500 is a possible combination. Most preferred one is M20 FE 500 because in the question paper all old papers FE 415 used. I'm going to solve with that, but hardly there will be slight variation. That's all. XU limit by D and all those things will be slightly different. Now observe here. This is a design, means this is all given in the problem. This is the data. What is your job? What is the job of a designer? He has to fix the cross section dimensions. He has to decide what is the value of B, what is the value of D, what is the clear cover. So design is a documentation. Okay, design is a documentation. You have to be very much careful in designing. You have to use the code books. Now observe here what you are doing in the design part. Observe here. So this is the data given. Now observe here. Design of singly reinforced beams. Data superimposed load or service load will be given, or it can be calculated. Either it is directly or indirectly given. Span is given. Material is given. One extra thing that I missed out is boundary conditions. Whether the beam is simply supported or cantilevered, that is also given. Now required, design the beam which includes calculation. See this cross section dimensions B and D, B and small d as well as capital D. Main reinforcement, how many bars of what diameter? AST calculation is there. AST has to be calculated. So cross section dimensions, AST, then shear reinforcement you have to provide. Find out the shear force, factored shear force from that one. Two-legged, let us say two-legged stirrups of so much of this diameter and spacing will be this much. So you have to find out diameter and spacing of stirrups. That is nothing but shear reinforcement. Then finally you should go for check for deflection. So here I have not included check for development length, which is optional actually. Sometimes they are asking, sometimes they don't ask. Check for development length. What is that one? I'll tell you later on. Whatever they're asking in the question paper for design, I will cover that one. Some additional part, I will cover it in the subsequent classes. Okay, so let us proceed here. I'll just go through the steps, how to solve it. Then I'll try to solve at least 3 steps today. I'll go to 3 steps at least. Now observe here. You have to refer some code books here. In order to design, code book has to be referred. For analysis, you refer less number of pages. For design, you refer more number of pages for design part. Now observe here, span to depth ratio. Let us say step number 1, what is given? Load is given, span is given. It is a simply supported beam has to be designed. Let us say like that. First step is cross-section dimensions. Then effective span and factored load has to be calculated. This I'll show you here. Means cross-section dimensions you have to finalize. It is based on page number 37 of IS 456. Span to depth ratios. If it is a simply supported beam, span by depth is 20. You know the span, now depth can be calculated using this ratio. Span divided by depth. Span by D is equal to 20 if the beam is simply supported. From this one, you know the span, you can find the depth. I'll show you that one, how it is done. Effective span and factored load has to be calculated. Factored load means you calculate the service load multiply by 1.5. It's called as factored or design load. Then find out factored bending moment and check for the depth and type of the beam. It means you have to find out the bending moment, which is WL square by 8 in this case. Then equate this one with moment of resistance, then find out the check for the depth. How to do that one I'll show you here. And type of the beam means whether the beam is under reinforced, over reinforced, or over reinforced or balanced. If the beam works out to be at the end of the step number 2, if you find that the beam is over reinforced, immediately you must discard it. You must change the cross section dimensions and all that. So over reinforced sections should not be designed. Okay, over reinforced sections should not be designed. Either it should be under reinforced or balanced section. Then step number 3 is main reinforcement AEST has to be calculated. For this one, page number 47 of IS 456 we will refer. Also the appendix formula. Whatever formula I have shown in the analysis part, that is appendix G. Again, we have to go there and have to check for the formula. Then shear reinforcement. Diameter of the two-legged stirrups and their spacing has to be given. Then check for deflection. Then finally, actually one more step is you have to draw the sketch actually. Freehand sketch should be drawn. Longitudinal section as well as cross section. So these are the steps in the design. Usually you can say 6 steps or 5 steps followed by the cross section and longitudinal sections. You have to draw freehand it is. Now observe here. What I have done here is just observe. Are you able to read this one? This is a first design problem of this module. Are you able to read this? Any one of you? Is it, can you read this one?
Yes, sir.
Okay.
Yes, sir.
Okay, let us say a simply supported beam of span 6 meter supports a service imposed load. Service imposed means it is unfactored load. Means service load it is. Safe load. A service imposed load of 12 kN per meter. Width of the beam is given as 300 mm. If width is not given, what to do? We'll come to know in the next problem. Here they have given the width of the beam as 300 mm. It is in the range of 230 to 300. For any structure, any RCC, It is in the range of 230 to 300 mm. You can get that also if it is not given. Support width is 230 mm. Width of the support is, the beam is resting on a support which is, width of the support is 230 mm. Design a rectangular section using M20 and Fe415 steel. Check for shear and deflection. So this is given now. So your job is to design. They have given the grades of the material. They have given the span and they say it is a simply supported beam, means boundary condition is given, span is given, service load is given. Whatever load that is acting, that is going to act on the beam is given. Now let us see the step number 1. See this one. Step 1 is cross section dimensions B and D we have to finalize. Now what we have done here is, remember one thing, design will not be unique. Everybody will not be having the same answer whenever a design problem is given. There will be slight variations. Only thing is that the value should come within the range specified in the code books. Somebody may use 550, somebody may use 450. As long as it is safe when it is checked, there is no problem. So design is not unique. There will be slight variations in the design from one structural engineer to another structural engineer. Only thing is that it has to satisfy the criteria given in the code book. So what I will do here is observe here. B is already given. Depth for this simply supported, I am going to use this range 112 to 115. I can directly use 1 by 20 also. but what since it is design is always a trial and error process. Now, in case of a simply supported beams, 112th to 115th of the clear span. Clear span is here 6 meters given in the problem. So what I will do first, I will calculate 1/12 of the span, 1 by 12 into 6 into 1000, because I want in millimeters. So 500. 500 I got. And one more trial what I have taken, the range is one more is, it should be in between these two. 1/15th of the span. It is 400 mm. 150. Now what I have done, out of this, I am trying as a first trial, I am trying with D400, whatever is there, no 115. Small d is 400. I told you design is not unique. You can try any dimension out of this. So what I will do is 1/15th of the span. Only after some practice you will come to know whether I should choose 500 or 400 in between these two values. Even if one can start small d 450 also. After solving some problems, you will understand it depends upon the load coming and all. Since the load is less here, load of 12 kN is not much. So 1/15th I have selected. So 400 mm. So I'm going to try as a first trial. D is 400. Capital D is add 50 mm in that. It is 450 mm. Now the dimensions are fixed in this one. These are all trial dimensions. Trial. They should satisfy all the checks. Now the dimensions are 300 by 400. 300 is width, 400 is the depth, total depth is 450. Okay, next. Now effective span has to be calculated. This is a term you observe here. So far we have not heard of this one. Effective span should be calculated. Observe this. Effective span is the smaller of center to center distance between the supports. So these are the supports. Clear span is given as 6 meter in the problem. They have given the width of the support as 230 mm. So this support is 230 mm. This side it is 230 mm. Now observe here. I need to find out effective span, because in order to use WL square by 8, that L is not 6 meter, that L is effective span. How to calculate it? You observe. Center to center between the supports. Effective span is smaller of these two. Just observe here. Smaller of this or this. Whichever is smaller, that becomes effective span. First one is center to center distance between the supports, which means center of this support, center of this support. So this is one possibility of effective span. One more is clear span plus effective depth. Clear span is inside, which is given in the problem. 6 meter plus small d is 0.4 meter. See this 400 mm is 0.4. So 6 plus 0.4 or 6 plus 0.23. So the smaller one is which one? Smaller one is this. So out of this and this you can see smaller one is 6.23. That has to be taken as effective span. WL square by 8 means W into 6.23 square by 8. Okay. So what I have done, center to center distance between the supports is calculated. It is 6. 6 plus 0.23 by 2 this side, 0.23 by 2 this side. So you can add 0.23. So 6 plus 0.23 is center to center distance between the supports, which was 6.23. One more is clear span plus effective depth. Clear span is 6 meter, effective depth is 0.4 because it is 400 mm. So it is 6.4 meter. So smaller is 6.2. Now next is load calculations. So I have fixed LE, effective span is 6.23 meter. Now I'll calculate the loads. Dead load. Dead load of the per meter you have to calculate. Kilonewton per meter I want. So dead load of the beam or self weight of the beam per meter length. 0.3 is the width, 0.5 is the total depth. It is density into volume into density. 0.3, 0.5 into 1 meter is the length. Per meter I have to calculate. Into density, volume into density. So dead load is 3.375 kilonewton per meter. Imposed load is given as 12. It is given in the problem. Imposed means live load. Imposed load is nothing but live load. This is imposed load, which is given. Otherwise, you have to assume this. In most of the cases, it will be given. Dead load you have to actually calculate after fixing the dimensions of the beam. Next, you can see here. Total, that is total load coming on the beam. Dead load plus live load is 15.375. One can use 15.4 also. There is no problem. That's why I told you design will not be unique. There will be some variations from person to person. Now observe here. So this is what is W is calculated. This is unfactored service loads. These two are service loads, unfactored loads. Now you can see, I'll go to the next page. W, just observe this. What I have done here is, I have multiplied that 15.375 by 1.5 because I have to put the design load. You cannot use service load to design. So because see 15.375 for the life of the structure, during the life of the structure, I'm not sure whether only this much load will come. That is why, to be on the safer side, I am multiplying this by 1.5, which is partial safety factor. So I have increased the load by 1.5 times. This is called as a design load because a lot of uncertainties are there for the 70 years of lifespan. Let us say I don't have any guarantee that only this much load will come on the structure. There may be some variations. That is why, to account for that, I am multiplying by 1.5. So this is 15.375 is unfactored load. It is called as unfactored. 23.06 is factored or design load. Now I have calculated the design load now. 23.06. 23.06 it is. Now step 2. In the step 1, cross section dimensions are done. Effective span is calculated, which is 6.23. Then design load is calculated. In step number 2, see here. So with this much of this one information, I am able to draw this figure now. 6.23 effective span. Design load is 23.06. Find out WL square by 8. Okay. WL square by 8. So W is 23.06 into 6.23 by square by 8. 119.119 kilonewton meter. Multiply by 10 raised to 6 because I want it in Newton mm. Similarly, factored shear force WL by 2. So W means WU here, factored load or design load 23.06 into 6.23 divided by 2. So I got it as 71.83 multiply by 10 raised to 3 because I want this value in newtons. Why this is required in newtons, we will come to know in the next step only. Now see here, this is find out MU limit. MU limit is 0.138 FCK BD square. This is for FE 415. So you need to see, you should be able to find out this one. If you forget this 0.138 in the examination, one simple method is there. You have to substitute XU limit by D in MU formula, which is there in the code book. Wherever XU limit by D is there, you submit that, you put that ratio 0.46 or 0.48, you will get this formula there. That you practice it, otherwise you remember this formula for limiting moment of resistance. Now what I have done is, after calculation of MU and VU, that is bending moment and shear force, maximum values of bending moment and shear force, I'm going to just separately, I'm going to find MU limit, which is 0.138 FCK BD square. You substitute all this. That is why I wanted bending moment in Newton mm, because this will be in Newton mm. So this is 132. Now compare these two. How do you decide whether the section is under reinforced or over reinforced here? You don't have to calculate XU limit and all in the design. Just compare this one with bending moment. See this. 111.9 into 10 raised to 6 is factored bending moment, whereas MU limit is this. So MU limit is more. You can see as MU is less than MU limit, section is under reinforced. This is a new thing that you are learning today. What is that new thing here? Just observe what is the new thing that you learned here is to decide whether the section is under reinforced or over reinforced. One more condition is also used, which is MU is less than MU limit. So far we were discussing XU less than XU limit, PT less than PT limit. Now this is MU less than MU. In design I have to use this one. Otherwise I'll be wasting my time in calculating XU and XU limit values. No need to calculate those two. And PT limit you cannot calculate here because I don't know how many bars of what diameter are there in the problem. I have to find out actually that one. So I have to use only this one. So MU is less than MU limit. See this. This is MU. Here it is MU. You can see this. This is MU. And this is MU limit. I think I'm clear, isn't it? Say this. This is MU limit. So MU is less than MU limit. So it is under reinforced. So far you were not knowing this actually. So far you were under the impression that XU less than XU limit, PT less than PT limit is enough. But here new thing is MU less than MU limit. So let us go to the next step. Now here I have calculated MU, VU and MU limit. Finally, I came to know that it is an under reinforced section. Now I can go to the third step. If I find that this MU is more than MU limit, it is over reinforced. That time I cannot go to step 3. I have to go back and revise the cross section dimensions. I have to make some changes. Then only I can proceed to step 3 because over reinforced sections are not allowed because the failure will be sudden. Step number 3, main reinforcement AST and check for minimum steel. Page number 47 of IS 456. How to find AST? Observe this. Now I have to calculate AST value. You can see how I have done here is I am going to use this formula. There are 2-3 formula you can use. Okay. This one is regularly it will be used. Somehow you have to remember this. See this. This is the formula I am going to use for calculation of AST. Okay. One more is available in the codebook. That is what is that? Annexure G. Whatever we have seen in the previous classes, that is there. I'll show you if you want that also. I'll show you. Now AST calculation. Area of steel I have to calculate it. 0.5 FCK BD by FY into bracket 1 minus square root of 1 minus mu. What is this mu? Observe here. After some practice, you will be able to remember this. Otherwise, you can go back to codebook and you use that one only. But that is going to take a lot of time. If you use that formula, I'll show you that also later on. Now, what is this? 0.5 FCK by Fy. In this problem, it is 20 by 415 B into E. 300 into 400. 1 minus square root of 1 minus mu. What I have done is I will calculate mu first in this formula. Mu is calculated first. So mu is 4.6 mu divided by FCK BD square. Carefully observe this one here. In this formula, mu is this. I'll calculate mu first. In some textbooks, they have shown as RB. Capital RB is given. I have used mu. Both are one and the same. Now for calculation of this, one more trick I am using. I'll calculate FCK BD. In this formula, see FCK BD is there. FCK BD square is there. But I will calculate FCK BD. Then I will multiply one more time D to get this denominator. Why this is done? Here also FCK BD is there here. Here also FCK BD is there. You can see that one. That is why this trick has to be used here. While calculation, first see this FCK BD. Now you look at mu 4.6 mu by FCK BD square. In this one, FCK BD is calculated like this. FCK is 20, 300 into 400. D square I am not doing an upgrade. So that I can substitute 2.4 into 10 raised to 6 here directly. See this. Directly here I can substitute. And for this denominator, what I can do? 2.4 into 10 raised to 6 into one more D. Into one more D. So that it reduces the calculation time actually. Now, now what I will do? After finding FCK BD here, I'm going to use mu calculation. So 4.6 into mu. See this is the actual bending moment, not limiting. It is not mu limit. Be careful here. It is actual bend WL square by 8. It is WU into LE square by 8. 111.9 into 10 raised to 6. So what I am doing now, I am calculating mu here. 4.6 into mu is this one divided by 2.4 into 10 raised to 6 is FCK BD. One more D I will add because it is D square. So this is 400. So FCK BD into one more D. So 0.54 I got it. So I got mu as 0.54. Just observe this. I got mu as 0.54. Now I am going to substitute everything here after finding mu. So it is 0.5 into FCK BD, which is 2.4 into 10 raised to 6. I'll put it here. Fy is as it is 415, 1 minus square root of 1 minus of 0.54. Observe here. What I have done here is AST equal to 0.5 into 2.4 into 10 raised to 6 FCK BD it is divided by 415 into bracket 1 minus square root of 1 minus mu 1 minus 0.5. So finally, after when you simplify this one, you end up with AST as 925.3 mm square. Okay, AST. One more AST which gives you in quadratic equation form. One more method is there. If you cannot remember this formula, after sufficient practice, you will be able to remember this. Because in most of the design textbooks or in wherever we try, this is used because it is not give you any quadratic equation. If you use codebook, I mean, if you use that codebook, you end up with a quadratic equation in AST. So there AST will be having two values. One of them will be 925.3. One more is one more value will be there. You have to choose any one out of that. So usually higher value is used. Then you use that quadratic equation. That I will show you later on. Later on, if you want to use codebook formula and try to find out AST, I will show you that also. Here, let us worry about this formula. So the way I have calculated, you observe here. I think there is any doubts in this one? Any doubts in calculation of AST? This is a totally new thing for you. It was not discussed in previous classes because AST was not calculated in case of singly reinforced beams in the analysis part. Okay, so 925. Now the next thing is directly don't use this 925.3 because code says AST should not be less than this value. So again find out AST by using this formula which is there in page number 47. I'll show you that one now. I may be having that one here. I may be having that page. It is here, see, 47 page number. I have it in these notes. I have taken only specific pages which are useful for design, not entire codebook. It is here, see. What I'm trying to tell you is this one. After finding AST by using that lengthy formula 926, you got it. Directly don't say it is final. Check whether it is more than this value, more than AST calculated using this formula. See this. Here what I will do, here I'll try to find out using this formula, this AS value. B and D, I know it. This is 0.85 divided by 415. From this formula, I will get AS again. So if this value is more than 926 something, I have to use this one only. Okay. Observe this one. Same thing I have written in the notes. Just observe this. What I have done is first calculate AST, then calculate AST minimum using that formula AST by BD into equal to 0.85 by FY. I got C, substituting all the values except AST, I got AST as 245. Now compare these two numbers, 245.8, 925.3. So whichever is more I should use. Out of these two, whichever is more. So 925.3 is more here. I am going to use that as AST value. So therefore, provide AST is equal to 925.3. So this 925.3, once this is finalized, choose either 16 mm or 20 mm bars. You can choose anything between 10 to 20 like that. For these beams, these are not heavy beams. 20 mm bar or less than that is enough. Now here also the design is not unique. Somebody may use 16 also. See, as long as he is trying to provide AST 925, that is why the answers will be different in the exam. Observe this. As long as he is trying to find out the bar number of bars and diameter, which will give AST very close to this number, it is accepted. For example, if somebody says I'm going to use 16 mm bars, let him use it, no problem. But you must see that the area is very close to this. If he chooses the number of bars of 16 mm, it should be very close to this number or slightly it should be more. Exactly will not get it because you cannot, whatever diameters are there, you will get that area. Now what I will do here is, let us say I tried with 20 mm. If somebody tries the 16 mm, there is no problem. So using 20 mm bars, number of bars, total area divided by area of one bar, total area of steel required divided by area of single bar. So it is 2.9, say 3 bars. If I use 3 bars, it will be slightly more than 925.3 now. Okay. Or you can try bar combinations. I will use 2 bars of 20 mm, 1 bar of 16 mm. I may come to very close to this. But in the examination, don't try that one. In practical life, they are trying. They will not give all the same 3 bars because they want to bring it very close to 920. Now what I have done, I am using same bars, 3 bars of 20 mm diameter. Now if you find out AST, which is 3 into pi by 4 into 20 square, it will be more than this. I need that value also later. Actual value also I need it. But here I will say I will provide 3 bars of 20 mm diameter. Okay, AST is calculated. Next, so AST is done, cross section dimensions are finalized. How many bars of what diameter is also there? Actual design is over now. Design is over, but still shear reinforcement is left. Only once the shear reinforcement is done, I can say design is complete. Then you have to go for checks. Step 4 is shear reinforcement. Again, I am using 73 page number, table 19. Okay. Now, how the shear reinforcement here? My objective is to decide the diameter and spacing of stirrups. Observe here. VU is WL by 2, 71.83 already calculated, 71.83 into 10 raised to 3. Now, how to decide? Now, what? As I told you, shear strength or shear capacity is sum of shear resisted by the concrete, shear resisted by the stirrups, shear resisted by the bent up bars. Here, I am not proposing bent up bars. I am not proposing bent up bars. I am going to find out the. Now, what I will do is just observe here how to decide whether shear is required or not. Now, you know that VU, which is WL by 2, is 71.83 into 10 raised to 3 Newton. Observe here. First, calculate TOSI BD, shear capacity of the beam. Okay. See, if the shear capacity of the beam itself is more than 71.83, no shear stirrups are required. That time you have to provide nominal stirrups, even if it is not required. Now observe here, let me check it. Shear carried by the beam, TOSI into BD. Let us find out TOSI. In order to find TOSI, you need PT and M20 as per table 19. So if you forget how to find TOSI, you remember table 19. In table 19, you will understand that I have to find PT as well as I have to check for corresponding grade. Now observe here. What I have done here is I need to find out shear capacity of the beam. For this one, I am going to use this formula, TOSI into BD. TOSI I'll calculate first. B and T already I know that. I know the values of these two. So PT. PT is equal to shear. 3. You cannot use 926 something there because that is for calculation of AST it was. Now actual AST is 3 bars of 20 mm diameter. So 3 into pi by 4, 20 square, that is AST divided by B into D into 100. So I got it as 0.785. Nearly it is 0.79 I have taken. So 0.79 is this. Now I will go back to the table 19. I already told you how to find it. So in the table 19, PT 0.75, M20 0.56 is there. For 1.62 is given as TOSI value. So for 0.79, what is the value of TOSI? I told you, you interpolate it. Interpolation diagram I have shown for you to refer. After interpolation, okay, TOSI for PT of 0.79 is given by complete interpolation I have done here. It is 0.57. So for 0.75, it is 0.56. For 1% of PT, it is 0.62. In this problem, PT value was 0.79. Corresponding to 0.79, after interpolation, the value of TOSI is 0.57. It is in between these two numbers. the value of tau c is between 0.56 and 0.62 because PT comes in between 0.75 and 1. That is why the value should be in between this. That is a check actually. You should check it. Once you interpolate and find the value of tau c, you check in this table. It should be between these two. That is important. So now 0.7 we got it. I can find out tau c into BD. Now observe here. Tau c into BD. Next page it is. See this one. Therefore, shear capacity of the beam without any stirrups, it is 68.4. Tau c BD is giving me a value 68.4 into 10 raised to 3. Now you compare this one with factored. How much is the shear force acting on the beam? Whereas the beam without stirrups is able to resist 68.4, but actually it is subjected to 71.8. Means if you do not provide stirrups, it is not going to resist because the shear capacity of the beam is 68.4, whereas it is actually subjected to 71.8. So the capacity is less. It means I have to go for stirrups, shear reinforcement. As Vu is more than VUC, it means factored shear force is more than the shear capacity of the beam without stirrups and without bent up bars. That is, VU is 71.83, VUC is 68.4, shear reinforcement is required. Even if the case is, even if this is less, even if this is more, this is less also, nominal shear we have to provide, nominal stirrups we have to provide. That I'll show you later on. In this problem, this is the situation here. So here the shear reinforcement is required. You have to find out the difference between these two. Because out of 71.83, beam is capable of taking 68.4. Find out the difference. For that difference, I need stirrups of the beam. Shear to be resisted by the stirrups. How much is the shear to be resisted? Because already beam is capable of 68.4 out of 71.83. So whatever is the balance, whatever is the difference between these two, that much is the responsibility of stirrups. Observe. So shear to be resisted by stirrups is factored shear force Vu minus shear carried by the beam. So difference in these two is 3 point, it's very small number actually, 3.43. So 3.43 is the shear to be resisted by the stirrups. Now use that formula. Use that formula on page number 73. So decide, you should decide 2-legged 6 mm or 2-legged 8 mm. It is left to the designer. It is your choice. That is 2-legged 6 mm. I'm going to choose. Somebody may say I'll use 2-legged 8 mm also. There is no problem. But you have to find out spacing accordingly. Either it will be 2-legged 6 mm stirrups or it will be 2-legged 8 mm stirrups. Only two possibilities are. 10 mm and all, they are not useful. The bending becomes difficult and which is not required also. 6 or 8 is enough. Now what I will do, I have decided 2-legged 6 mm stirrups will be used. What is the spacing now? You have to use this formula. This formula is there on page number 73. It is there or no? There it is, VUS was here, SV was below in that formula. So I have interchanged, I want SV here because FY I know, ASV I know. ASV is 2 times pi by 4 into 6 square. D is already there, 400. VUS, what is this? VUS. This VUS is difference between the factored shear force and the shear resisted by the beam alone. This difference should be substituted here. That is 3.43 into 10 raised to 3. Like this, you substitute all and find out the spacing. Spacing is coming very big because the value of this is very small. 3.43 is a very small number. I got 2380 mm. You just check it, check it later on. Anyway, this is not used. This is not used. Now again check it. But spacing for nominal shear, that is spacing, should not be more than whatever this formula is giving. Where is this formula again? Page number 48. Now what we have done here is using this SV, VUS is equal to all this from page 73. I have found out the spacing. I cannot use this one directly. I should check for one more form. It should not be more than this. Using this formula, you calculate SV. Observe here. Observe this one. See, this is SV is here. Now you have to open page number 48. Then there is this formula is there. In this formula, find out SV. So how much it is? It is giving me 170. 170 it is giving. So whichever is smaller out of these two, whichever is smaller out of this number and this number, that value should be used for the spacing. Okay, is it clear, this one? So you can, I'll show you this one if you want. Same thing I have done in AST calculation. AST is calculated compared with one formula given in the code book. It should not be less than that. But in spacing I have used this formula from page 73. And again from page 78, I checked with one more formula. I calculated SV there. So this SV and this SV, whichever is smaller, that should be taken. So I calculated SV like this by two methods. 170 is smaller. So this is 170 I'll be using. But again, the spacing should not be more than 300 mm. Should not be more than 0.75D, which is 0.75 into 400. Or should not be more than whatever value I have calculated just now. Out of these three, the smallest should be chosen. One is should not be more than 300 in any case. It should not be more than 0.75D, 0.75 into 400. Or it should not be more than this number, which is just now calculated. It is here, see. It is here. Out of three, the smallest should be selected as a spacing. Smallest is 170.05. So I'll round it off. What I will write? Hence provide two-legged 6 mm stirrups at 170 center to center as shear reinforcement. So this is how shear reinforcement is done. Any questions are there, you can ask here. I am going to stop it now. In shear reinforcement, any doubts are there? What I have done? In shear, what I have done? See here. In shear, first I have calculated WL by 2 because it is simply supported beam with UV. So actual shear force to be resisted is 71.83. Now I checked whether beam itself is able to resist or what. I checked whether beam itself can take this much of shear force or not. I checked the shear capacity of the beam, which is tau c BD. So tau c BD is calculated like this, PTA and all this, using table number 19, and interpolation is done. Finally, I will get tau c as 0.57. From this one, I'll calculate tau c BD. And I'll compare this tau c BD with 71.8. Okay. Since tau c BD was less than 71.83, beam itself will not resist shear. So I need stirrups. So why the stirrups are required? Because tau c BD is less than 71.8. It is here. So tau c BD is 68.4. It is less than 71.8. Stirrups are required. So in order to find the stirrups, you should subtract this and this, 71.8 minus 68. See, it is here. Now this value is used. This value is used here in VUS. I think this formula already you know it. If you open page 73, only changes VUS is here, SV is below. I have just interchanged VUS and SC. That's all. Remaining all the same. So VUS is difference of these two 3.43. But it is giving a very huge, very big spacing actually, which is impractical. So impractical value I'm getting. That is why I need to check the spacing should not be more than this, which is given in page 48. I'll show you that one and I'll stop it. Where it is, I'll show you. Page number 48 is here. Only those pages I have taken. Using that website, I can remove specific pages. It is here, see. Minimum shear reinforcement. Minimum shear reinforcement in the form of stirrup shall be provided such that this formula is set. This is what I used there actually. I used this formula only. ASV by BSV is equal to 0.4 by 0.87 Fy. Here in this formula, I try to find out SV. All other things are known there. So this SV and that SV are compared, whichever is smaller is selected. Following one more condition. What is that one? One more condition is, carefully observe this. I'm going to stop now. After finding these two, okay, page number 48 and all, again, it must satisfy this criteria. It should not be more than, for example, this value and that value, both are giving more than 300. This is also more than 300, that is also more than 300. That time you have to stick to 300 only. It means in any case, the spacing should not be more than 300. In any case, if the value is coming less than 300, use that. So also spacing is 300, 0.75 times D. Then actual calculated this one, 170. Okay. And also you must compare with this value also. This is very impractical. This value is impractical here. So I'm going to choose 170. I'll round it off to 170 center to split. 170.0 something is there. I'll round it off. Finally, shear reinforcement is completed. On Saturday, I will complete last step, that is deflection check. Okay. So all of you, I think you have given your attendance there. So in between, somebody has taken the screenshot, because some students are just entering in USN and all chart, then they are disappearing, some students. So at any point, the person is taking the screenshot, your number should be there actually. When the screenshot is taken, at that time your number should be there. If it is not there, means you have just typed your USN and in the chat box and you are not there. That should not happen. So I'll end this class now.
Sir.
Tell me.
Sir, ಅದು 0.85 ಎಸ್ ಅಂತ ಇದ್ರಿ ಸರ್, ಅದು 56.62 ಅದು ಎಲ್ಲಿಂದ ತಗೊಂಡ್ರಿ ಸರ್, ಗೊತ್ತಾಗಲಿಲ್ಲ.
One second. I'll go back. You just check it. Which number? Yavu shear? Yavu step? Which step?
Sir, R ಅಂತ ಹೇಳಿದ್ರೆ ಸರ್, ಅದು step.
No. In shear or in bending moment?
Shear, sir.
Shear, no? Okay. This page, same page, no? Same page?
Yes, sir. Yes, sir.
You are having some problem with spacing,
Sir.
Is it related to spacing here? See, you can see here. First, use the usual formula given in page number 73. Find out SV. You are getting some number, let us say 2380. Okay? Is there confusion? Same?
Sir, the 0.87415 into 56.52 sir. 56.52 the ಎಲ್ಲಿಂದ choose ಮಾಡ್ಕೊಂಡು sir.
Okay. You are asking this one. ASV, you are asking. ASV calculation here I have shown. See this. ASV is 2 times pi by 4 d square. Because I have selected see, I am choosing this 2-legged 6 and 5. You can choose 2-legged 8 also. If you use 2-legged 6, 5, ASV is 2 times pi by 4 d square, which is 56.52. 2, I have used 56.2 here. You are
Okay.
talking about this, isn't it? This number.
Okay.
This number
Yes.
is this one only, no? See this. It is, see, it is my choice. I have selected 2-legged 6-5 stirrups. If we use 2-legged 8-5, the ASV will be different. It is 2 into pi by 4 into 8 square agtado. Right now I am selecting 6 mm. Okay, that's why I told you design will not be unique. It can be slightly different also, but it should come within the range given in the code books. Now ASV is this 56.52. D is 400. Is it clear now?
Yes, sir. Okay.
Okay. Now I will end this class. Any other doubts? See, this video I will upload it and notes I will give it. The problem is, and attendance is very low. 83, 84 students are attending the class. I'll end the class now. Any doubts are there? In the next hour, Saturday morning, we'll discuss. Only one step is left. That is deflection check.